Alright, so in this video we're going to learn about gravitational potential energy, and we are going to start looking more into how to use the conservation of energy to solve problems. So we're going to start with our work energy theorem, and now we know that there's two different types of work because there are two different types of forces. So this is work non-conservative, so this would include work due to forces like friction and air resistance, and work conservative, which are forces that are path independent. And then that equals the change in kinetic energy. So we're going to split our work conservative into a force times a displacement and plug in the force due to gravity for our force. And since the force due to gravity acts only in the y direction, we're going to multiply it by delta y, because remember the force and the displacement have to be parallel to each other. I've now subbed in for the force due to gravity, so that's mass times acceleration due to gravity. Remember, this is negative. And then delta y is always y final minus y initial. And then I've just distributed the mass times the acceleration due to gravity to both terms. So we end up with work non-conservative plus a negative mass times g times y final plus mass times g times y initial equals the change in kinetic energy. This allows us to define that the gravitational potential energy is equal to mass times 9.8 times the height, or distance, from a baseline. So we're going to call this the gravitational potential energy. And anytime you have a potential energy, it's stored energy relative to the baseline. So in this case, it's stored energy against the force due to gravity. But you have to define where your 0 point is. So where are you setting y equals 0? So that's important to set it in a problem and leave it there for the entire problem. Alright, so all I've done up here is I plugged in for the change in kinetic energy 1/2 mass times velocity squared minus 1/2 mass times velocity initial squared. So let's write that a little bit bigger on the next page. It's just going to look like the next section of the video, but it's the next page for me. And what I've done is I have added this here to the other side, and I've added the kinetic energy initial to the other side. And this is going to allow me to have all the initial energy on one side and all the final energy on the other side. So let's look at that. Alright, so we have initial kinetic energy plus initial gravitational potential energy plus the work non-conservative. And the work non-conservative is going to be the force non-conservative over the path that force is applied. And that is not going to always be the same thing as delta y. So you actually have to look at the path that the object experiences that particular force. And that is going to equal then 1/2 mass times velocity squared. So that's going to be your final kinetic energy plus your final potential energy. So we can summarize this as saying that we have an initial amount of mechanical energy plus or minus a certain amount of work non-conservative. So we should really put a minus sign in there. Now most of the time for me, something like force due to friction and air resistance is going to be negative. You can write problems where the work non-conservative is positive, but I tend to write problems where the work non-conservative is going to be negative. And that's going to equal your final mechanical energy. So if you have work non-conservative in the system, energy is lost or gained from the system. Now, mind you, once again, the energy is not magically appearing or magically disappearing. It's just being transferred in or out of the system through non-conservative forces. However, if you have no non-conservative forces, then mechanical energy is conserved, so your initial will equal your final. Mechanical energy is conserved. And so you can see that your initial energy has to equal your final energy. Now there's one thing I want to talk about, and if you look up here, I've now stuck a box over the work non-conservative. So let's pretend that there's no work non-conservative. So we're ignoring air resistance, we're ignoring friction. And imagine you have an object falling through the air. Now when you look at each of these terms, you can see that there's mass in each of them. And in algebra, if you divide each term by the same quantity, that is a legal algebra move. So I can divide each of these terms here by mass, and the mass will cancel out of each of those terms. So it turns out the mass doesn't matter. It isn't until you start getting work non-conservative that it actually matters, because then you'd have to divide that term by m, and it would matter on what the mass is. And I'm going to link a video in the next slot in Blackboard where you can see a bowling ball and a feather dropping. And you can see the difference in how they behave based upon whether or not there is air resistance and when there isn't air resistance. And that's going to play into the conservation of mechanical energy.